All right, let's get into it. Today, we are diving headfirst into one of the deepest, most mind-bending riddles in all of mathematics. Seriously, this is a problem that pushes right up against the boundaries of logic and asks a question so strange, the answer actually changes what it means for something to be true.
So let's just start with the big question right away. Can a mathematical statement be both true and false? It sounds impossible, right? But that is exactly what we're going to explore. We're going to look at a famous statement about infinity that, depending on the mathematical universe you decide to play in, can be proven 100% true and also, just as rigorously, proven 100% false.
To even wrap our heads around this, we have to start with the guy who first dared to measure infinity, Georg Cantor. Back in the late 1800s, he came up with this brilliant idea he called cardinality. It was basically a clever way to compare the size of infinite collections of things by seeing if you could pair every single item from one set with an item from another.
And using this method, Cantor found the first, most basic level of infinity. He gave it the symbol Aleph null. This represents the size of the set of all the counting numbers, 1, 2, 3, and so on. Sure, the list goes on forever, but you could theoretically list them all out. That's why it's called a countable infinity.
But then, Cantor did something that just blew everyone's minds. Using his famous diagonal argument, he proved that some infinities are just, bigger. The infinity of real numbers, that's all the numbers on the number line, including every possible decimal and fraction, is so huge, so dense, you literally cannot make a list of them. It's a whole different beast, an uncountable infinity, which we now call the continuum.
So this is where the puzzle really takes shape. We've got our first infinity, Aleph null, the countable one. Then we have this vastly larger infinity, the continuum, which we call C. And just for context, C is also the same size as 2 to the power of Aleph null, which is a whole other story. And then there's this theoretical next size up, which mathematicians just call Aleph 1. It's defined as, simply, the very first infinity bigger than Aleph null.
And that leads us straight to the 100-year-old mystery. A question so important, it was literally the #1 problem on David Hilbert's famous list of challenges for all of 20th century math. It's called the Continuum Hypothesis, and it's deceptively simple. It just asks, is the continuum the very next size of infinity? Is C the same thing as Aleph 1? Or is there some other intermediate size of infinity lurking in between?
For decades, the greatest minds in math just slammed their heads against this problem. Nothing. Then, in 1940, the absolute legend, Kurt Gödel, came along and made the first real crack in the case. But he did it in a really clever way. He didn't prove it was true in our universe. Instead, he built a special, custom universe where it had to be true.
Gödel's whole strategy was about one thing: restriction. He decided to build a version of mathematics that was as minimalistic as possible. He stripped everything down to only the sets and numbers that were absolutely essential, getting rid of any potential fluff. He called his creation the constructible universe, or just L. Okay, think of it like this. Imagine building all of math with a basic set of Legos. Gödel's universe only uses the simplest, most fundamental bricks. No weird, fancy, or custom pieces allowed. And the amazing thing is, this universe works perfectly. It follows all the standard rules of math. It's just really, really tidy.
And here is the punchline. In this super clean, minimalist universe that Gödel built, there's just no space for any weird intermediate infinities to exist. The very construction of it forces the continuum to be the very next size up from the integers. It forces C to equal Aleph 1. So Gödel had shown that it is totally consistent with the axioms of mathematics for the continuum hypothesis to be true.
But hold on, that's only half the story. The world now knew the hypothesis could be true, but did it have to be? Decades later, another brilliant mathematician came along with a completely new and revolutionary technique to answer that exact question.
In 1963, a mathematician named Paul Cohen came at the problem from the complete opposite direction. Instead of restricting the universe like Gödel did, Cohen figured out an ingenious way to carefully and consistently expand it.
He invented this wild, mind-bending technique that he called forcing. It's basically a toolkit for surgically adding new numbers into an existing mathematical model without breaking anything. It's like a master architect figuring out how to add an entire new skyscraper into the middle of a city without causing any of the surrounding buildings to collapse. It was truly revolutionary.
So, using this new forcing method, Cohen built a brand new mathematical universe that was also perfectly consistent. But in his universe, he managed to cram in a colossal number of new real numbers. So many, in fact, that the size of the continuum, C, was now way bigger than Aleph 1. In this new expanded reality he built, the continuum hypothesis was definitively false.
And this, right here, just perfectly lays out the incredible dilemma. You've got Kurt Gödel, who builds a lean, tidy, minimal universe where the hypothesis is true. And then you have Paul Cohen, who builds a rich, expanded universe where the hypothesis is false. And the craziest part? Both of their universes are completely valid and consistent with all the fundamental rules of math.
So what on earth does this mean? How can a statement be provably true and provably false? This is where we arrive at the stunning, profound, and final verdict on the continuum hypothesis.
You know, this answer didn't just appear overnight. It was the result of a journey that took almost 100 years. From Cantor first asking the questions, to Hilbert putting it at the top of the list, and finally, to Gödel and Cohen delivering these two bombshell proofs that completely redefined the limits of what mathematics could even do.
So when you look at it all laid out like this, the situation is crystal clear. We can build a perfectly logical, consistent mathematical world where the continuum hypothesis is true. And we can build an equally logical, consistent world where it's false. From that fact, there's really only one possible conclusion. The continuum hypothesis is undecidable within our standard foundation of mathematics, which is called ZFC set theory. And this is so important. It's not that we just haven't been smart enough to find the proof yet. No, it means that the very rulebook we use to do math, our core axioms, is fundamentally incapable of giving us an answer. The rules just don't cover it.
So where does that leave us? I mean, if the rules of math can't decide, what's the real answer? This is that amazing moment where pure abstract logic crashes right into philosophy. You have to choose what you believe.
Probably the best way to think about this comes from the history of geometry. For thousands of years, everybody just assumed that Euclid's geometry was the one and only true geometry of the universe. But then, mathematicians realized you could create totally different, but still perfectly consistent, geometries where parallel lines can meet. The big discovery wasn't that Euclid was wrong, but that other, completely different geometrical realities were possible.
So this forces a huge philosophical choice on you. Are you a Platonist? Do you believe that there's one single true mathematical reality out there and our current rulebook is just incomplete? Or are you a formalist? Do you believe that math is more like a system we invent and that there's a whole multiverse of different but equally valid mathematical realities we can choose to explore?
And believe me, this isn't just a fun debate for philosophers. Right now, today, mathematicians are actively searching for new, powerful axioms they could add to our foundations. A lot of the research is focused on things called large cardinal axioms. These describe infinities so mind-bogglingly huge that they tend to create a much richer, more maximalist kind of universe. And the general feeling among many in the field is that if one of these new axioms is ever accepted, it will almost certainly lead to a universe where the continuum hypothesis is false.
So in the end, we're not left with a simple answer. We're left with a much, much deeper question. The continuum hypothesis basically showed us a crack in the very foundation of mathematical truth, forcing us all to ask, what is math, really? Are we explorers discovering the map of a single true reality? Or are we architects inventing beautiful new worlds of our own design?